Alright, so in this particular problem, we have a box of mass 76 kilogram hangs motionless from two ropes. It says in the diagram below here, it says the angle alpha is 40 degrees. So it's the angle alpha that touches the vertical axis by the dashed line there. That dashed line is your vertical axis. And it says choose the box as a system, calculate the magnitude of the tension in each rope. Alright, so let's go ahead and do it. As usual, go ahead and identify your tension in each of the ropes. Here are two ropes. Rope 1, label rope 1. I'm just going to draw that pointing leftward because that's that's tied to the wall. And then rope 2 is going to be pointing towards the ceiling. And that is going to be T2. Okay, since the diagram calls it rope 1, I'll call that T1, and it says rope 2, I'll call that T2, just to keep the subscripts consistent. But here it says the angle alpha is 40 degrees. So make sure you pay attention to how angles are given to you. But let's go ahead and crack out T2. T2 is a diagonal, therefore it has to have a T2x in this case pointing to the right, and it has to have a T2y which is pointing up. T1, as you notice, is just perfectly in the horizontal direction pointing leftward, so it has no components because it's pointing perfectly along one of the directions. Alright, I like to go ahead and label 40 degrees is given to me here in the statement. It says angle alpha is 40 degrees. So I like to point out that this angle here touches the vertical axis. It's up to you. You can totally keep 40 degree as your reference point, but I like to encourage you to use the angle that touches the horizontal axis. In this case, I've chosen to use 50 degrees because this is a right coordinate, this is 90 degrees between the y coordinate and x coordinate system here. So if this is 40 degrees, the leftover has to be 50 degrees because you take 90 minus 50, so that angle there is 50 degrees. I like using the angle that touches the horizontal axis because it keeps my cosine and sine geometry consistent. All right, you don't have to though, so I'm just going to use 50 degrees instead of the 40 degrees given to me. Okay. Alright, the next vector that you should always draw out is the weight of the mass. In this case, it gives us mass, which is 76 kilograms. So pay attention to units as you practice. This is 6 kilograms, so that's M. Sometimes problems gives you the weight of the system already, so make sure you don't multiply by 9.8. So if you're given the weight, which is in newtons, do not multiply by 9.8 because then you would do 9.8 twice, okay? So here's the vector f of g, which is pointing straight down the page, and that's in blue. So let's go ahead and do all of our components for T2. T2 in this particular problem is the only tension, or only force that has any sort of component, because T1 is pointing perfectly leftward, f of g is pointing perfectly downward, and then T2 is diagonal. So let's go ahead and do T2x and T2y. T2x is your adjacent leg. Is your adjacent in geometry is cosine. Cosine of angle here, again, I've chosen to use 50 degrees. It's your adjacent over hypotenuse. So T2x is the adjacent to this angle 50 that I'm deciding to use over hypotenuse, which is T. So for T2x allows me to move T2 to the left side, which makes it multiply, or you can multiply both sides by T2, and then the denominator cancels out here, and then T2 goes up to the top left. Okay. And then I can do the same skill for T2y, referencing the 50 degrees angle that I've chosen in orange. T2y is my opposite, and opposite in geometry is sine. So sine of 50 degrees is opposite, which is T2 over hypotenuse. This is the only reason I like to use, the angle that touches horizontal axis in math. Cosine is x and sine is y, as long as your angle touches the horizontal axis. All right. Solving T2y, you do, which is multiply both sides by T2. So therefore T2y is simply T2 sine of 50 degrees. All right, now that we have the components for T2, let's go ahead and set up the physics. We know for these types of problems, the system is at rest. Therefore, net force in the x direction has to equal to 0. So in this diagram, pretty straightforward. You have T2x pointing rightward, and then you have T1 pointing leftward. So I will do my positive vector first, the vector component first. In this case, T2x is positive, so I'll write T2x first. And then I'm going to subtract it from T1 because T1 is negative. So here I'm stating that T1 is indeed negative. So I'm subtracting, but I'm subtracting a positive value, whatever T1 is, or the magnitude T1, okay? Isolating for T2x. T2x is already positive, so I'm going to keep that on the left side of the equal sign. I'm going to move this negative T1 to the right side. So therefore T2x is equal to T1, but T2x can be substituted out for T2 cosine of 50 because in this little box here in the center, T2x is T2 cosine of 50 degrees. And if you simplify in the calculator, cosine of 50 degrees is about 0.643, and then T2, don't forget to carry that down. So we have an expression here with two unknowns, T2 and T1. So we can say that T1 is 0.643 of T2, whatever T2 is, okay? It's up to you whether you isolate for T2 or T1 here. It doesn't really matter. I'm just going to keep it the way it is because T1 is already by itself. All right. Let's go ahead and set up information in the y direction. Excuse me. In the y direction, I have T2y pointing upward, and then I have f of g pointing downward. So therefore, those are the only two arrow or vector components that I see for this particular problem. Okay, so T2y point up, f of g point down. So therefore, I'm going to write the positive ones first. T2y is positive. I want to subtract that from f of g. Here, I've stated that f of g is already pointing down, so pay attention as I substitute in for g later on. So to solve for T2y, I'm just going to move this negative f of g to the right side of the equal sign. That'll change the sign. And then T2y can be broken down into T2 sine of 50 degrees based on this little square in the center here. T2y is T2 sine 50 degrees. All right, so you notice here I substitute out for f of g in terms of mass times gravity. I know the mass is 76 kilogram because it's given in the statement here. The mass is 76 kilogram that I'm circling back and forth on the top left of the screen. And I know what g is, okay? So therefore, I can just solve for T2 simply by dividing both sides by sine of 50 degrees. So it'd be mg over sine of 50 degrees. Here we know everything. We know m is 76 kilograms. We know g is 9.8 meters per second square. And then sine of 50 is just some decimal on your calculator. So if you punch all the stuff in, you notice here, m is replaced with the value given. G, however, is positive 9.8 because earlier in the second line in the y direction, I already said that it's negative f of g. So this is usually sometime where kids, struggle with, okay? So here I'm going to use positive 9.8, and then the sine of 50 is just 0.766 on the calculator. And if you do all this, you get a value or magnitude of about 972.3 newtons. And that would be our answer since it's just a magnitude. And here's the statement that hopefully will help you remind yourself to use positive 9.8 and not negative because the negative sign has already been accounted for. All right. Now that we know what T2 is, okay, so T2 is about 972.3 newtons. Now that we know T2 is, we can just go back from our work in the horizontal direction. We can find T1 because we said earlier that T1 is 0.643 of whatever T2 is. Well, now we just found T2. So now that we found T2, we just substitute it in. So it'd be 0.643 times 972.3, and all that calculated work will give you a value of about 625.2 newtons for T1. So those are our two answers. So T2 is 972.3 newtons, and then T1 is 625.2 newtons. All right, other than that, stay nerdy. Don't be whack.